California, and good morning or good afternoon to all of you wherever you happen to be. My name is Amir Jose Macari. I'm Dean of the College of Engineering and Computer Science at California State University in Sacramento, and I'm also the director of the California Smart Grid Center. With me is also Dr. Suresh Vadva, who is the chairman of the Department of Electrical and Electronics Engineering and Computer Engineering, as well as research director of the California Smart Grid Center. So if you have some questions along the way, we'd be very happy to answer them for you. Let me start with a presentation today that I've titled Power and Telecommunications Engineering in the Context of Smart Grid. First of all, let me start by saying electric power plants have been in operation for, over a century. If Thomas Jefferson was to be today here, they wouldn't notice too many differences from the operations that were ages ago, other than it is massively distributed throughout the country, and electricity now reaches everywhere in the world. We see some examples here of the typical power plants. We see up in the left-hand upper corner hydroelectric plants, which throughout the world produce a lot of electricity. We see gas operating plants. We see coal-burning plants, as well as nuclear power plants. This is a slide that is very complicated, obviously, but let me just talk about a few aspects of it. This was developed by Lawrence Livermore National Laboratories, which is a national laboratory of the Department of Energy of the United States. And what we see on the left-hand side of the screen is the sources of energy and percentages of how much energy we're consuming from the different types of sources. And what we see on the pink side, on the pink squares, is where all of this electricity ends up going. As we know, obviously, petroleum is the largest source of energy that we have, but we see that massive amounts of it obviously go into the transportation industry. Vehicles, cars, airplanes, and so on. And about 10% of the total energy from petroleum also goes into industrial applications. Now we see biomass. Oops, I'm sorry about that. I'm going to have to be careful with my mouse. It seems to be a little sensitive here. Okay, what we see on the other side of the screen is coal. The coal, 22%, and this, but very, very similar percentages are throughout the world. Coal burning plants, which are very polluting, are almost strictly used for electricity generation. Natural gas, well, you see that there's a diversity of uses for natural gas, and it burns a little bit cleaner. But then we go towards the other areas where we know that they are the renewables, including biomass, geothermal, wind, hydro, nuclear, and solar. Nuclear, obviously, it's not necessarily a renewable energy. It's not a renewable energy, but it is a significant energy that is used for electricity in some countries more than others, at some times in history more than other times. Right now, obviously, after the disasters that occurred last year from the earthquake and tsunami in Japan, nuclear is being very carefully examined to see if that is a viable, continued source of energy that we need to use. This slide is a little bit more international because I noticed when I was just looking at it a little while ago, it's actually in Spanish. So bear with me. All it indicates is that many of these sources of energy produce greenhouse gases that obviously are impacting our environment. And this slide right here really is the one that shows the effects. What we see at the top, obviously, is that we're going to look at CO2, and on the other end of the plot, we see it in temperature in degrees Celsius. So parts per million carbon dioxide, temperature, degrees C, and we go back in history to 1,000 years ago. So from 1,000 years ago unto about right now. And what we notice is that there were oscillations in temperature, there were oscillations in carbon dioxide. The temperature variations were very, very slight until we get into the Industrial Revolution, when industrialized nations begin to use coal, begin to use petroleum, fossil fuels, and we see that over the last 100 years, this increase in temperature and in greenhouse gases has increased exponentially, way beyond any expectations and way beyond anything that is manageable. We as humans have really made a negative impact. And people can argue all they want to, but these oscillations over 1,000 years, you notice that there's not much change until, again, the era of the Industrial Revolution. A lot of it obviously has to do with the United States, Britain, Germany, France, Italy. But more recently, China and India have really been some of the ones that have contributed a lot to the increase as well. So it is a national but an international problem as to how we are able to control this. And I'm not going to get into the environmental aspects of it, but we do know that increase in temperatures are causing glaciers to melt, are causing sea levels to rise, are causing natural disasters to be of larger magnitudes, and we're just not capable of addressing these problems, and something has to be done. So as part of that, California has taken one of the most aggressive environmental legislations in the world. In 2007, it became known as Assembly Bill number 32. It was passed even though there was a lot of opposition from a lot of lobby groups, especially, obviously, oil companies. But California has always been an innovative state that wants to think about the future, and we depend very much about this because we have very important coastal cities that would be affected by the rising sea levels, such as San Diego, Los Angeles, San Francisco, and so on. So the idea behind AB 32 is to prevent this continued increase of temperatures and to eventually try to halve it, to reduce it in half, so we will only be able to see in 30, 40, 50, 60 years a maximum rise of about 2 degrees centigrade. That 2 degrees centigrade is still a very dangerous number, and us as engineers, we're going to have very big challenges to be able to address the problems that are created with that. However, if we do nothing and continue to abuse Mother Earth, what we will see is a tremendous rise in it and something that nobody will be able to repair in the future. So that's the context of what we're looking at. Early in the 1950s, refrigeration in the United States was using about 350 kilowatt hours per year. Of course, between the 40s and the 70s, just the use of refrigeration increased drastically per refrigerator unit, because refrigeration went from almost ice boxes to very complex, very fancy refrigerations that also use freon and other gases that are considered to be greenhouse gases. Fortunately, federal legislation suddenly came in, again by California standards, and throughout the 70s and 80s, those regulations insisted on making refrigeration a lot more efficient, a lot more economical, and a lot less polluting. You continue on throughout the years going that way, and we see that finally, as we approach 2001, major federal standards came in, and now we require every refrigerator to be a lot more efficient. The only problem here, though, is that if we look at the pink line down below, this is a line of estimated standby energy kilowatt hours per home. That is, all of those devices that we have in our home that are simply standing by, ready for us to use at any second, just push a button and go. None of those existed throughout the 40s, 50s, 60s, even 70s. And suddenly, in the early 80s, we started to really notice a difference. A lot of VCRs came in, a lot of microwaves came into our homes, a lot of different devices started coming in that had what we call little vampires, because they live at night when nobody's noticing them. The problem is that those devices have now permeated our homes and are continuing to be a major increase of energy usage. And that is an area of research that we all have to address very carefully. Today, for example, the cable box that I use in my home to receive television at high energy, HD, high definition, just standing by uses almost a quarter of the energy that a refrigerator uses in full mode. So there's a lot of work that needs to be done in those sorts of devices in order for us to be able to control this curve and bring it back down to very small levels and not impact as it goes forward. Per capita energy use in the United States has increased over the years as well, from about 4,000 kilowatt hours per person per year in the 1960s, and 65, 70. It continues to increase, although since the 90s it has tended to flatten out a little bit. But we see that two states in particular, California and New York, which are the two states that are the most advanced and that usually are very aggressive with energy regulations, have done a lot better, to the point that we have now leveled off this curve, and hopefully in the future it will even begin to drop. If we look just in California, actually this is in our city where I am from right now, Sacramento, California, which is the capital city of California. This is where the seat of government is. All our senators are here, all our Congress people are here, our governor is here, and all of the major agencies are here as well. I'm sorry, something popped up. We'll block it off. And what we see that in throughout the year, typically in winter months and spring months, we're not using a lot of energy. But come summer, when the heat starts coming in and we all turn on air conditioners and kids are home from school all the time and the televisions are on all the time, our energy consumption is incredibly high. But there are only a few days that we do that. Now, in order to prevent outages, we have to design our power supply to at least be able to reach this highest level. And this is in megawatts, by the way, 21,000 megawatts. So there's a large use of energy, and we have to keep on power plants, building power plants if this bar continues to grow. The issue is that only 50 hours are representative of energy used during those peak times. That is, if we were able to just build power plants to about this level, 14,000 megawatts, we wouldn't have to have so much energy consumption, and especially polluting energy. So we have to address this and try to flatten this curve towards the end. This is just if we go back, I'm going to blow this portion up just so you see it in big letters. And you see that is that portion right there, expanded over, and it represents 10% of the annual generation. But it is only for 50 hours a week in the entire year. 50 hours in the entire year represents 10% of the annual generation. That seems to me very inefficient, and that's why we need to take care of this area. How can we do that? Well, energy efficiency, modern technologies, all of those things that we're going to be trying to talk about today. And that's where the subject of today's lecture is about smart grid. What is smart grid? Well, before I get into smart grid, I want to tell you a little bit about our center that we developed here at the California State University in Sacramento, also known as Sacramento State. 3.5 years ago, 4 years ago, we began this area because our power engineering program is the best and most respected power engineering program in the entire state of California, and certainly likely to be the most important power engineering program in all of the western United States. So we formed the Smart Grid Center because we had power engineering, and the idea is for the Smart Grid Center to be a product testing center where a lot of industries come in and test their products before they are deployed to the field. We want to be a center that does research in an unbiased way. That is, we will not sell out to large interest groups, large companies. We are here to serve the public. Third, the center will support the California's utility companies. We have some of the largest utility companies in the country, 3 of them that I'll mention in a little bit later. So we want to help them develop and design those highly desired upgrades to the centuries-old electric grid in order to lead us to the creation of the Holy Grail, basically, smart grid. The center will also focus on workforce development. After all, we are a university, not just a research institute, and we want to be able to develop the professionals that will be able to carry out all of this work throughout the state, throughout the country, and throughout the world. Let me just give you a synthesis of what is smart grid. Well, smart grid is a generic label for the application of computer intelligence and networking abilities to the decades-old electric distribution system. Smart grid initiatives seek to improve operations, maintenance, and planning by making sure that each component of the electric grid can both talk and listen. A major component of smart grid technology is automation. When we talk about talking and listening, we're talking about controls and sensors. We want to be able to develop a grid that is almost like seeing an avenue or a major metropolitan city. Imagine it running without any traffic lights. It would be chaotic. if you go to Los Angeles and not have any stoplights, any traffic lights, any way to control the traffic, it would be total chaos. Well, that in a way is what the electric grid is today. So we want to install all of these sensors and control capability by using, again, computer intelligence and networking, and embed that into the electric grid. One of the advantages of being in developing countries, I'm originally from Mexico, so I can tell you about that, is that power engineering is still a very important discipline in my country because it is still evolving. There are still many regions of my country that are not reached by the power grid. There are many communities around my country that don't have the luxury of electricity. Well, as we expand the electric grid to different regions, we want to be able to ensure that it is done now with the latest of technologies, and that's what I would hope to see in other developing countries as well. Let me give you just a slight explanation of smart grid from a schematic point of view. What we see right here is the standard generation from power plants, nuclear, natural gas, petroleum, coal, hydroelectric. More recently, we began to introduce wind power, solar power, and coming in and generating at very large megawatt facilities, generation. Well, that electricity then gets transmitted through very high voltage cables, very high voltage infrastructure, until it reaches substations where the voltage is controlled, is reduced, then sent and distributed throughout neighborhoods, and goes into eventually transformers outside of your homes, and they reach your meter outside your home, and of course provides electricity inside the house. What we're doing now is beginning to have a lot of solar rooftop generation, so we are generating electricity not only at the central plants, but we're also generating it at many other regions from across the region. In addition, we're going to be having electric vehicles. These electric vehicles are going to have to be plugged in, and the old system is going to be overwhelmed very quickly. So now what we're going to have in our homes is hopefully a lot of times storage. So we're going to have batteries and inside the homes, but we also need to have industrial type storage at the utility scale in order for us to be able to store electricity in the substations and be able to shut down generation when it's not needed, hence not polluting anymore, and making everything a lot more efficient. So how can we do that? Well, the only way to be doing that is to install communications and networking throughout. So now smart grid is not going to be an area that is exclusive to power engineers. We are now going to need computer engineers, we're going to need computer scientists, we're going to need networking people. There's going to be a lot of folks that are needed in here. And any time that we begin to do wireless communications, the biggest problem that comes in is obviously cybersecurity. Everybody's scared about what could happen to a system if we get attacked in a terrorist attack. No longer a 9/11 type of attack where somebody goes in and blows up an airplane into a building. Now they can render an entire region powerless and without electricity, and we know that today, without electricity, none of our handheld devices or our computers would be able to work. So this gives you a schematic illustration of what smart grid is all about and why is it so important. And I hope that by now it's piqued your interest and you're thinking, okay, maybe I wasn't thinking of power engineering as being important. As a matter of fact, power engineering in the United States virtually disappeared from universities in the late 80s and 90s because it was considered to be a mature discipline, that no new research was going to be done and no new people needed to be educated in that area. However, right now, we see that all of this new equipment and all of these new technologies come into play. Fortunately, the California Smart Grid Center continued to have power engineering. California State University at Sacramento continued to have power engineering as a discipline. And right now we sit in a very ideal place to compete not only with other universities in California that may be much better known, such as USC, University of Southern California, Stanford University, University of California, Berkeley, University of California at San Diego, many of those very powerful universities that everybody knows around the world. They're calling us now to try to partner with us and do research with us because we are holding on to a very important discipline that they can't just suddenly ramp up and build for themselves. So again, I hope I'm piquing your interest in this area, and I'll go on and discuss a few more subjects. All right, inside the home. So let me go back again. We've talked about all of the infrastructure outside of the home, but we know that inside the home there's a little meter that sits right there on the outside, and the old analog meters simply go with the old technology that has been around from General Electric for 50 or 60 or 70 years already. And now we're seeing the birth of new meters. These are called smart meters because they look very similar, but now they're digital, not analog. They're able to still measure the kilowatt hour usage that is going into the home, but they're also instrumented with two different radios. Two different radios that transmit wirelessly. One of the radios transmit back to the utility company, so the utility company can tell if your electricity is out or is on, and also be able to measure day to day how much electricity is being used at every little home in the country or in the region of that particular company, and be able to make better decisions, more strategies. The other radio signal transmits inside the home, and it will be transmitting to a box similar to what we would think of a cable box for television, but we call it an IP energy gateway. That IP energy gateway is just the same one that we will use for our internet. So we have our computers and everything controlled there through the routers. But we will also be able to communicate with cameras, again the routers, IP phones, our plasma TVs, all our lights, as well as any kind of lighting control and heating and cooling inside the home. Those are going to be the key elements of the smart grid inside the home. So what we're doing again is empowering the user to be able to address how much electricity each one of these devices is using and when to better use it. In the future, electricity is not going to cost the same at every hour of the day. Why? Because we know that at 5 or 6 o'clock, when most people go home and turn on their electricity, turn on their TV, their air conditioning, their ovens, their washing machines, we end up using so much electricity that it is very costly to use it then. So it is going to be priced at different periods of time, and it is something that people will be able to say, okay, I know that electricity is going to cost 5 times as much to use at 5 o'clock, but I want to watch my television. I don't care. Well, that's an informed decision that you as a consumer can make. Some other people may say, well, I'm going to wait until midnight to wash dishes or to wash the clothes in our homes in order to use electricity at a different period of time when it is a lot cheaper. And the question has always been, why Sacramento State? Again, why not USC? Why not Stanford? And why not Berkeley, University of California, Berkeley? And my answer has been very simple, is because we are the perfect choice. We have a very strong program in power engineering. We have a very strong program in cybersecurity. And we have a very long history of renewable energy and solar energy research and education. So with those three components, it would be like having a table with the three legs right there. You take one of those legs off and the table falls. Fortunately, we have the three legs, and that's why I feel we are the perfect choice. In addition to that, we have been, as some of our researchers and our professors have been aging and retiring, we have been able to complement them with new hires, and I'm very happy with some of the researchers that I'm listing here. I'm not going to go through each one of their names, but I'll talk a little bit about them a little bit later. In addition, we have professors in our staff that are the authors of some of the most important power engineering books in not only the country but around the world. These books have been translated to different languages and are used as textbooks and as reference books for research as well. I mentioned a little bit a while ago that we have a lot of expertise in cybersecurity. Well, the first thing that I did when I came to this university 6 years ago was to work with the faculty in computer science and understand that we had capabilities in cybersecurity. So we applied to the National Security Agency in the U.S. Department of Homeland Security to have Sacramento State College of Engineering and Computer Science designated as a center of academic excellence in information assurance and security. We've completed a 5-year period, and right now we're about to be granted our next 5 years. This is a very highly visible entity, center, that has received accolades from everywhere in the country, especially from Congress in the United States. And we all know that cybersecurity is not only important for smart grid, perhaps it's even more important for other issues such as telecommunications, banking industry, and so on. So I'm very happy to have this group with us, and people come to us and ask for our advice all the time. Students get to work hands-on with our professors, learning the latest methodologies and latest techniques as to how to be able to prevent attacks from cyber terrorists that may be looming out there. It goes to the importance that President Obama has made statements on cyberspace policy. And he says, as the United States deploys new smart grid technology, the federal government must ensure that security standards are developed and adopted to avoid creating unexpected opportunities for adversaries to penetrate these systems or conduct large-scale attacks. Well, this was a policy that was instituted a couple of years ago, and just last month I went to Washington, D.C. and sat in Congress as they discussed cybersecurity. Some of the biggest experts in the world were there, including Symantec, McAfee, all of the different companies that are very, very good at cybersecurity. They were there providing testimony to Congress to see how this country and how the world can be a lot more secure in cyberspace. I mentioned earlier that the California Smart Grid Center, we partner with all of the utility companies in California. The three on the left-hand side of the screen, Pacific Gas and Electric. Pacific Gas and Electric is perhaps the second or third largest energy company, electric company in the country. Southern California Edison, provides electricity to most of the Los Angeles basin and regions like that. San Diego Gas and Electric to all of San Diego and regions surrounding it. Our particular utility company, it's a smaller one. It's municipal, and it's called the Sacramento Municipal Utility District, and we partner with them very much to do a lot of research. We're actually doing some research right now on the cybersecurity aspects of their new smart meters that have been installed throughout our region. Burbank Water and Power, we provide also expertise in cybersecurity, but also in power and sensors and controls. One of the nice aspects of our program at the California State University in Sacramento is that we bring a lot of industry through our two big organizations, IEEE, the Institute for Electrical and Electronic Engineering, and PES, the Power Engineering Society. Industry is very, very interested in our graduates from companies throughout the region, including Intel, Cisco, Google, Facebook. All of them are very interested in what we're doing because they want to go into that space eventually. This is just a list of some of the courses that we offer for a Smart Grid certificate, including courses in electrical engineering, that we have power systems, energy systems control and optimization, power distribution, electromechanical laboratory, smart grid, renewable energy, and integration of that renewable energy into the grid, smart grid electric powers, power systems, and so on. We also have mechanical engineering courses at the bottom that bring in heating, air conditioning, solar energy, alternative energy, and high efficiency HVAC. And finally, the third leg is the computer science courses, in which we have computer networks, telecommunications, internet security, computer forensics, countermeasures and attacks, cryptography, and finally, computer forensics. The full array of courses just in power engineering that we have at our university, including undergraduate and graduate courses, are 23. Now, 3 of these courses are always recommended as the core courses, base courses for anybody that studies electrical engineering. Electromechanical conversion, power systems analysis, and power electronics. But now we're going to begin to add other things to our curriculum, including relay protection and, as I mentioned earlier, the home area networks. That is the networking that's going to occur inside your home to be able to take advantage of this issue of smart grid. Our online certificate courses are growing right now, and we're looking forward to having most of these online sometime within the next 6 months or so. Several of our professors are now working daily in our studio, ensuring that these courses get put online, and we start out with very basic introduction to power systems. The reason that we do this is because nowadays electric companies are beginning to hire computer scientists, IT professionals, networking people, and they don't speak the same language as electrical engineers and power engineers. So we need to have a course that levels the playing field. We want to work then on future power systems and smart grids, distributed generation and renewable generation. That is, not only is it going to be renewable sources such as wind, solar, and biofuels, but they're going to be generated in many different areas and no longer at the central location where the power plant used to be the only place where we would generate electricity. We're going to have courses in interconnection standards. We're going to work on microgrids and islanding, the issues regarding, obviously, distributed generation. We will work with power systems and automation. And finally, smart grid data communications. All of these courses we hope to have online within the next 6 months. And we have received funding from the U.S. Department of Energy and to be able to do this. The Secretary of Energy is very keen on us being able to produce the next generation of power engineers that are able to understand and able to bring forward the dreams that we all have of smart grid. This is just a look at some of our power engineering laboratories, perhaps very similar to some of the ones that you're studying with. High voltage in the sense that, you know, we can go up to 400 volts. Students readily work with these things, with this equipment. We have relay protection equipment. And if you look at it in detail, they look very similar to what was many professors of yours took 30 and 40 years ago. The only difference is, obviously, the infrastructure, the insides of it are very similar, but now we're able to connect them to analog to digital interfaces, and we're able to control, monitor, and do data collection, data acquisition in a digital format. So let me talk a little bit about some of our research projects so you get a flavor of the type of work that we are currently doing. First is modeling the development of load control strategies and the integration of electric generators. I'll talk a little bit more in detail about each one of these very soon. Building to grid technologies, evaluation and developing a roadmap for our state. Smarter power grids with green resources, and this is done a project in collaboration with another national energy laboratory, the National Renewable Energy Laboratory in Colorado. We've working with the Air Force as well to show demonstration projects of what are the nuggets, what are the great things about smart grid, because the Air Force happens to be the largest consumer of energy in the entire world. Of course, much of it goes on high-octane fuel for the fighter jets, but the Air Force uses tremendous amounts of electricity as well, and they are under a mandate by the government to reduce their carbon footprint and to become a lot more energy efficient. We're working with this idea of microgrids and the integration of renewables and placement of storage. What we're looking at here in microgrids, just to give you a little flavor of what this is about, it's basically that we want to be able to have specific regions that may not be able to be reached by the electric grid, a national electric grid, but be able for them to be able to generate their own electricity and control their own loads and their distribution. So in order to do that, we need to help them integrate renewable energy into their system, and we have to help by placing storage at strategic locations. Another project that we have is with Cisco Systems. Cisco is very interested in this, and you would think, why Cisco? Why would they want to work in anything like this? Again, everybody in the high-tech industry sees a smart grid as a space that they want to move into because they see that as the future of our country as the United States tries to become energy independent and eventually not have to go to wars over oil because we will be sufficient with our own renewable energy. Smart grid cybersecurity issues, we have major projects in that area. And finally, we're doing monitoring and investigation of sample electric loads in a microgrid, in a subsystem for the future automated distribution networks. I showed you a little while ago some of our faculty and some of our staff working in the project. I would like to first highlight Professor Suresh Vaiva, again, who is right here next to me. He is a computer engineer by trade. He got his PhD in computer engineering, and more recently, over the past 5 or 6 years, he has really aggressively gone into learning everything he can about power engineering and how to incorporate his knowledge in computer engineering for the benefit of power engineering, hence calling it smart grid. He is the chairman of the Department of Electrical and Electronics Engineering, and is also the research director for our center. We have researchers working in information assurance, technology, and security. That is cybersecurity. So we have a very large group, some of them working in cryptography, others working in devices to make them a lot more secure, some of them working in software engineering to ensure that the software that is being used for these telecommunication devices is secure. In the area, continuing on, we have professors in the area of controls and robotics, solar thermal technologies, power systems, photovoltaic, wind, biofuels, sensors and instrumentation, and of course, as I mentioned before, a very strong group in power systems and power electronics. Now, to date, we have completed several projects, and I just want to go through the research project that we're working on. First, our first introductory year, about 3 years ago, we began working on research analysis of building to grid communications. That is, how can a building in all of its different electric systems inside the building, from lights to computers to printers to telephones to the HVAC, the heating and air conditioning, ventilation, all of it, how can it communicate back to the grid? Well, for this particular project, the University of California, Berkeley called us in to help them with it. We were the experts in this project, and it's always nice to see that a renowned university calls on to you for help. That obviously says something about your capabilities. We installed insulation and weather stations for renewable resource metrics. We've done research analysis on renewable resource integration standards. Standards is a very big thing right now because we don't want to go the same way that the VHS and the Betamax went, where there were no standards. We don't want to go through the same wave of issues that the United States and Europe have, different electric standards. We want to make sure that the standards are not only interoperable within a region, within a state, within a country, but that they become worldwide usable. And finally, we did the creation of research laboratories for device testing. This was our first introductory year. We had perhaps a handful of graduate students working in the projects, but now on second year, third year, we've increased that work. We have many more students working in our research laboratories. We're doing a research analysis of estimated electric vehicle impact. What if an entire neighborhood decides to buy electric vehicles? How will that impact the utility company and the infrastructure that goes with it? We have gone, in addition to Air Force bases, and have done energy efficient retrofits into their existing buildings, even kitchens with more efficient equipment, more efficient lighting, and communication devices, so everybody knows what every device is consuming at any one point of the day or the year. So when we're talking about energy management and building to grid technologies, we worked, I said a few minutes ago, at the University of California, Berkeley, the last couple of years. It was funded by the California Energy Commission. The research test bed was a building that was 200 square feet, and the energy usage was about 1 megawatt hour per year. It was very old and inefficient ventilation, so it turned out to be a very good test case scenario. They created wired and wireless networks of sensors, large volumes of tag data relating energy consumption to time of day. The data was stored in simple monitoring and action profile databases, so we would be able to analyze what was going in those projects. And the result has been a very successful project that UC Berkeley has heralded as a tremendous success. So we've ended up publishing a number of papers, not only for our researchers, but researchers with our students, and the students have gone on to do other projects as well. Renewable energy resource and standards. The research that we're currently doing is at the utility standards. First of all, we have to do a lot of literature search. We have to gather and document current standards, interconnections, and distribution resources. For that, we end up using a lot of undergraduate students who we again hire to do some of our work. We are looking at the standard practices of some of the larger utility companies, investor-owned utilities. We work with the California Public Utilities Commission, so we investigate the rules and regulations currently in place, and we are proposing newer standards for them to use in the future. The California Smart Grid Center publication on renewable resource integration. We have published how many papers in this, Suresh? 8 papers, and again, many of our students are co-authors in this area. Plug-in electric hybrid impacts. This is an area that obviously is impacting already in California. California is looking at selling many, many more electric vehicles. Soon, I will be getting a Volt, Chevy Volt, which is an electric vehicle, plug-in hybrid, and these electric vehicles are not only non-polluting because they are not using any fossil fuels, only in case when the electricity of the vehicle runs out, but at the same time, they're making this country a lot more energy independent. And we will not be worried about the variations of oil prices, which are wreaking havoc all over the world these days. We're looking at estimated impact for neighborhoods going in and adopting a lot of these vehicles. So the project goals are to determine the California utility providers concerned on increased penetration, that is, of more electric vehicles there, analyze the concerns and mitigate plans by the California regions, unify the consensus of electric vehicles replacing light-duty vehicles. And again, we are publishing quite a few of these papers on the impacts to utility companies. Beale Air Force Base, as I mentioned before, the project was to do lighting and non-lighting technology retrofits to improve energy consumption. The dining facility that feeds 3,000 military personnel and operates every day, 24 hours a day, all year long. We needed to bring in much more efficient devices that also are able to communicate with the smart meter to show how much electricity is being used, and other sorts of retrofits as well. The current research projects really are the most exciting as I see it. Once we've become comfortable and once everybody saw that we were a very successful research entity, they started asking us for a lot more work. This particular one volt var or volt variations is a project that we're working with the very large utility company, Pacific Gas and Electric. It is to study the impacts of renewable energy generation at different periods of time. As we know, a cloud can just go over a solar panel and render that solar panel useless for the time that is under the cloud. So electricity really comes and goes. We want to be able to develop possible methods of mitigation. We will have another project in which we're working on is sensor networks, in which using national instruments, wireless sensor nodes, as a platform to gather building data. That is, we want to know all of the information inside a building: temperature, humidity, light, CO2, anything that will get us data in order to make a lot more informed decisions. Local energy generation, storage, and distribution. The use of simulation of integrated systems along with real data in order to create test beds for energy management control algorithms. So this project is also developing software that can be embedded into the devices and operate in order for us to better understand local energy generation, its storage, and how that energy is being distributed. Information integration. This one is working really with our local utility and working with large databases in order for them to, because again, smart meters are going to be generating gigabytes of data, and utility companies are not set up for that. The only data that they ever had was data once a month when the meter person would go into the home and write down the number of kilowatt hours that had been consumed over that month. They would send it. They would then collect it by hand, put it into Excel sheets, and bill the customer. Nowadays, we're going to be looking at gigas and terabytes of information. And we are also looking at a project right now with a major Australian company that has its headquarters, North American headquarters, here in Sacramento. It's GridSense, where we will be installing sensors on the distribution lines in order for us to be able to tell quickly and easily if there's a fault, if there's a problem, what sort of signal is coming through that distribution line. That is, what is the voltage isolation of that signal, and what is the frequency, and what is the frequency changes of that signal. We want it to be as stable as possible in order for us not to, first of all, blow transformers or prevent outages in a region. So again, this is going back to the voltage variations. The negative impacts of voltage variations is that as we generate energy that is from renewable resources, solar, as I explained, when clouds go over, they get covered up. Wind is very quirky. It doesn't work all the time. So we're generating electricity intermittent. And the power flows. So we need to be able to control it, clean the signals, and be able to send it on along the way. The research project is really seen highly by our current governor, Governor Brown. I almost said Governor Schwarzenegger. That was our previous governor, Governor Brown. And the mandate is for us in California to generate 12 gigawatts of renewable energy in the near future. So the project goals are, first, to better understand the effects of renewable and distributed generation on the electric utility grid. identify potential tools and methodologies to help us monitor and control those loads, find effective line regulation techniques to cope with sharp photovoltaic fluctuations, and investigate impacts on utility companies and the grid protection systems as a result of these fluctuations. The system energy network integration is really what we're wanting to do is an energy management system. We want to integrate sensors for environments such as room temperature, gradient, and humidity mapping, CO2 saturation trending. We want to be able to have then integration of solar insolation weather stations, control energy paths using historical and real-time data in order for us to be able to better adjust to what is happening in the field. I spoke about microgrid and microgrid integration. This is really a 3-year project, and it's had 3 different phases of the research projects. The first one is the project goals are to investigate the viability of large-scale renewable resource integration using microgrid topology. Let me tell you a story of what happened the day that the earthquake and tsunami occurred in Japan. As soon as it occurred, obviously, Fukushima nuclear power plant had to be shut down. Everything was shut down, and an entire western region of Japan, northwestern region of Japan, went without electricity. Now, the worst thing that you can do in a disaster recovery is not to have electricity, because you're not able to do anything once the light goes off. However, there was in the little town of Sendai a microgrid that was being operated there only as a demonstration project. That microgrid obviously went offline as soon as the earthquake occurred, just like virtually everything did, but the microgrid came back within 15 minutes, and that was the only source of electricity that the entire region had. So this is a success story for these projects to investigate the viability. And the way we're going to do it again is phase 1, modeling local generation, storage, and distribution. Basically, we're going to be medical doctors. We're going to go and look at the body and take blood samples, do an EKG, look at how your brain pattern is working. That is exactly what we're going to do first, to understand all of the criteria and get the data in order for then us to be able to make a diagnosis and propose devices and methodologies to work on. So once we validated the model, collected all the data of the critical systems, then we will begin to design hardware and begin to integrate it into the system. And finally, once the doctor feels very confident with the diagnosis, we go in and do small-scale hardware demonstrations and eventually have a full-scale design integration validation. What that will be is that our entire campus at the California State University in Sacramento will become a microgrid, and we will be generating and distributing and operating all of the electricity on our campus. We're doing a lot of work with street lighting monitoring, and again, this has to do with sensors and controls. We work with some of the major companies in the region and also with other universities in California. As a matter of fact, one of our sister institutions, the University of California, Davis, has a very strong center in lighting technology, and they always want to work with us because they know the lighting portion of it, but they don't know the power engineering portion of it. So that's what we want to work on. We want to street light monitoring. Again, all of these wires that we mentioned before, the distribution wiring, will be adapted with sensors from GridSense, and we will be able to detect street light faulting anytime, anywhere, and not have to wait until other people tell you that electricity is no longer there. So the project is going on. How many students do we have working in this project? 6 students working in the project. How about on the microgrid project? Have we started this project yet? Two students are working in this area. Okay. Just to show you a little bit of what our students are, this is not a posed picture. It was taken while they were working on their laboratories. They're there doing the work hands-on, so electric companies really like the type of students we're doing, because they're not just computer simulators and cubicle-type engineers. They're able to go in the field and propose solutions and work with field engineers and technicians to come up with viable solutions. And we're very proud of the students that we're developing these days. So as we reach some parts of the conclusion of this lecture, I think I may have gone a few minutes past. The question really is, can we help create the smart grid? Can we help develop the future generations of engineers, scientists who will help us combat global warming? And the answer that I gave to President Obama is that yes, we can. And we're working very hard with them every day. I would be very happy to take some questions now from all of you. And as we do that, let me see if I can show a couple of pictures. And let's see if you recognize some of these folks. Do you recognize this person? Probably not with a tie, but with a machine gun at his hand. That's our former governor, Governor Schwarzenegger, who, by the way, has been a tremendous supporter of smart grid and energy efficiency and clean technologies. Governor Schwarzenegger now has gone back to the movies, and probably you will be seeing them at your local theater in the near future. Let me see if I see a couple of other pictures down here. Okay, yeah. This one was from about a month ago. Oh, let me move this from here. This is me taking a picture of the president as somebody's taking a picture of me. I was there at the White House, invited by the president, because President Obama wants to ensure that we generate many, many more engineers. Not only that, the president is aggressively trying to pursue legislation that says that when we graduate a master's or PhD engineer, even if they happen to be from a different country, that we should do everything in our power to be able to provide them opportunities to work in the United States for as long as they wish before they return to their country, because we need that expertise. It is no longer going to be this issue of graduating and having to leave the country. The president is very aggressive in looking at helping American companies be able to keep this incredible talent that comes from all over the world, as the United States have been known for a long time. Okay, well, I'll show this one. This one was my own picture with my own cell phone, taking it. As the president was turning the other way, I figured I'd take advantage of that, and so I could have a little memory of being there at the White House with them.